What's up everyone? Welcome back to this video lecture in probability theory. Okay, so in this video, I am going to discuss about moments and moment generating functions of a random variable. Okay, so we start with some definitions. Okay, so we have the definition of the arith moment and the arith central moment of a random variable x. So we denote by x the random variable. Its arith row moment is denoted by mu sub r prime and is defined as the expected value of the arith power of the random variable x, or e of x to the power r, provided that the expectation exists. Okay, now this arith central moment of x about the mean. Okay, so if we're going to get the central moment of x about its mean mu sub x, then we denote that by mu sub r. Okay, so walang ano lang, tinanggal lang natin yung prime. So pag merong prime, notation yun for the row moment. Pag wala, yun yung central moment. But anyway, mu sub r is just the expected value of x minus the mean mu sub x raised to the rth power. Okay, and also we have the rth factorial moment of x. Later we can make use of this factorial moment in our succeeding discussion. Okay, so the rth factorial moment of x denoted by mu sub bracket of r, where r is a positive integer, and is defined to be the expected value of x times x minus 1 times x minus 2, etc., times x minus r plus 1. So this is actually the following factorial of x of degree r. Okay, so we get the expected value of that. That is defined to be the rth factorial moment of x. Okay, and the qth quantile of a random variable x denoted by psi sub q is defined as the smallest number psi that satisfies the cumulative distribution function of x evaluated at that number psi is greater than or equal to the number q. Okay. So let us now define the before that, let's have some example. So we have the expected value of a random variable x raised to the third power is, this is the third row moment. The expected value of x to the 4 is the fourth row moment. Now, if you can recall from our previous video, we defined the variance of a random variable x to be the expected value of x minus its mean, which is just e of x to the second power. So in other words, the variance of x is simply the second central moment of x about the mean e of x. Okay, so we now define the moment generating function, or MGF, of a random variable x. Okay, so the expected value of e to the tx, okay, the expression e to the t times the random variable x, is defined to be the moment generating function of the random variable x, and we typically denote it by small m sub x of t. Okay, so the moment generating function is a function of this new variable here, t. That is provided that the expected value exists for every value of t in this interval from negative h to h, where h is some positive number. Okay, so if x is discrete, then we can write the moment generating function, since it is just an expectation, as the sum of e to the t times xj times the probability that x takes on the value xj for all j. And when x is continuous, the moment generating function may be derived by integration. Okay, so it's the integral from negative infinity to positive infinity of e to the tx times the density function f sub x of x times dx. Okay, so later we will discuss why the expected value of e to the tx is called a moment generating function of the random variable. So from the name itself, we must be able to generate the moment of a random variable using the MGF. Okay, but before that, we will illustrate first how to derive moment generating functions of a discrete and a continuous random variable. So in the first example, we have a random variable x with probability mass function given by p to the x times 1 minus p raised to 1 minus x times the indicator that x takes on the values 0 and 1 only. Okay, so we can easily get the expectation here because x takes on only 2 values. Okay, so the moment generating function m sub x of t is, again by definition, the expected value of e to the tx, or since x is discrete, then it is just the sum of e to the tx times the PMF p sub x evaluated at x. So since x takes on only values 0 and 1, so when x is 0, we will have e to the t times 0, and then the PMF is this one, so when x is 0, we will have p to the 0, 1 minus p to the 1 minus 0, plus when x is 1, we will have e to the t times 1 times p to the 1 times 1 minus p to the 1 minus 1. We simplify that one and we will get 1 minus p plus p times e to the power t. Okay, so this is the moment generating function of this random variable x, whose probability mass function is given by this one. Okay, for a continuous random variable, let's consider this probability density function. So it's e to the minus x times the indicator that x is non-negative. Okay, so x takes on only positive real numbers. So the moment generating function is the expected value of e to the tx, or by definition, the integral from negative infinity to positive infinity of e to the tx times the density function will then be the integral from 0 to infinity of e to the tx times e to the minus x dx. So since this is an improper integral, we're going to write this as a limit. So it's the limit as a approaches infinity of the integral from 0 to a of e to the t minus 1 of x dx. So we just combine these two exponential expressions here, or functions, and that will just be e to the t minus 1 of x. And the antiderivative of this expression is e to the t minus 1 of x divided by t minus 1. And we evaluate that from 0 to a, which are the limits of integration. But then we have to get the limit of that expression as a approaches positive infinity. So when we substitute a and 0 to this expression by the fundamental theorem of calculus, we will get this one. Okay, and then we get the limit of this. Here we do not have an a already, so this is now independent of a, but here we have an a, so the limit of this will be 0 provided that t minus 1 is negative. Okay, so when this is 0, we will be left with this expression, and that is just the negative of 1 over t minus 1, or simply 1 over 1 minus t. But again, this limit will exist if 1 minus t is greater than 0, or t minus 1 is less than 0. Okay, therefore, the moment generating function of this random variable x with PDF given by this function here is 1 over 1 minus t, provided that 1 minus t is greater than 0. Okay, so the next theorem, actually, this one tells us that this gives us the idea that the moment generating function actually helps us in generating the moments of the random variable x. So the theorem says that if the moment generating function exists, or if the moment generating function of a random variable exists, then mx of t is continuously differentiable with respect to the variable t in the interval negative h to positive h for some positive number h. And if we're going to differentiate the moment generating function r times with respect to the variable t, and if we let t approach 0, we will obtain the rth row moment of the random variable x. In other words, the expected value of x to the r, or the rth row moment of x, is just the rth derivative with respect to t of mx of t evaluated at 0. Okay, so for example, from the random variable x in the second example, so we have let me just rewrite the density. It's e to the minus x I 0 to infinity of x. Okay, it's mgf is equal to 1 over 1 minus t, and we can just actually write this as 1 minus t raised to negative 1. So if you want to get the first row moment, okay, so for the expected value, or the mean, the mean is just the first row moment, we just have, this is, r here is equal to 1. So in this case, we just have to get the first derivative of mx of t. So we'll have mx of t prime is equal to negative 1 times 1 minus t raised to negative 2 times another negative 1, or simply 1 over 1 minus t squared. Okay. The expected value of x, according to the theorem, is just mx, the first derivative of the moment generating function evaluated at t equals 0. So that will just be 1 over 1 minus 0 squared, and that will give us 1. For the second row moment, we will have r is equal to 2 here. So we need the second derivative of the moment generating function. So since we knew already the first derivative, we can easily solve the second derivative of the moment generating function with respect to t. I will just write this into 1 minus t raised to negative 2. So the derivative will be negative 2 times 1 minus t raised to negative 3 times negative 1, or 2 all over 1 minus t raised to the third power. So the expected value of x squared is equal to mx double prime of t evaluated at 0, so that will be 2 all over 1 minus 0 cube, and that is equal to 2. Okay, now if you want to solve for the variance of the random variable x, we know that the variance is the expected value of x minus its mean, right? But what is the mean? The mean is just 1, so squared. However, we know that this is just equal to the expected value of x squared minus the expected value of x quantity squared. So from above, the second row moment is just 2, while the first moment, or e of x, is just 1. Square that 1, so that will be 2 minus 1 is equal to, so the variance is also equal to 1. Okay, so I guess that's all for this video. We will have more examples on this when we proceed to our next discussion. See you in the next video lecture.